Hello everyone, I'm Michael Wu. I was responsible for both the procedural content generation and artificial intelligence aspects of this project. For my part in procedural content generation, I've decided to generate a grid of what I'll call blocks that act as a terrain for the future AI system to traverse. It will allow for a range of customizability, including island and continent landmass generation, as well as some other utilities for the terrain, such as Poisson disk sampling and infinite generation. I chose this topic because I wanted something that looks and is fundamentally simple, but has an incredible depth that will make it a worthwhile development challenge. To begin, I have simple polar noise calculation which determines the look of the terrain, simple green blocks to act as grass and grey blocks to act as impassable mountains. This is generated using Unreal Engine's built-in F-Maths 2D polar noise. Depending on the value returned by the noise function, we can spawn a specific block. This will serve as our humble beginnings. It does look a little plain, however. It'll be great if we can change up the map a little so that it doesn't look like a giant clump of land. The first thing that came to mind were continents or archipelagos. We can split the terrain up into either large or small sections to form land masses, similar to that of our Earth. This function to generate continents or archipelagos is quite similar to placing blocks, the major difference being that it runs off of a different offset value than that of the placement of blocks, a different scale value and an added split distance value. It'll run another polar noise function using these different settings and apply the value to the given grid position. As a result, we'll store these values that make up the water values of the map and return the T-array. Once that is done, we can subtract the polar noise value before placing blocks. As a result, the map will have been generated with these new continents in consideration. It still looks a little bit basic though. I don't quite like how the edge of the map immediately cuts off into the void without any warning. There needs to be a defined border surrounding the map so that it can look a bit more natural. If we look at some images of countries like Australia, we can see that they are all surrounded by something called water. Something like this is called a Falloff generator, where the values of the edges are subtracted, such that the placement of blocks and its polar noise value will be in line with generating water. Here is the function. We go over every possible point of the map and find out how close this point is to the edge of the map. We can do this by computing the xy components of this point and have it divided by the total xy components of the map. Then we want the point that is closest to the edge, that is the maximum of these two values. However, it turns out that the island nations tend to have water completely surrounding them, but this method here only gets us the closest value to the most northern and western borders. So we need to clamp it to be between -1 and 1, so that we get information about the southern and eastern borders as well. And here is the result. There may be a slight problem, however. Our Falloff generator is a little too influential on the map at the moment. What we want is an equation that lets us control the strength of the Falloff map at a given point. Consider the function f of x is equal to x to the a divided by x to the a plus the quantity 1 minus x to the power a. Clamp a from 1 to, let's say, 5, and we have a nice curve that we can control with the strength of Falloff. The evaluation of this function is 0, it means that land can spawn. Where it is 1, it means that the Falloff value will have a greater and greater influence on the map. However, this doesn't give us much control over the land points. If we multiply 1 minus x by another variable b, we have much more control of the curve as it lies along the x-axis. This is essentially controlling the bias of the Falloff generator. Instead of directly setting the value closest to the edge, we want to set the value to the function we've just made. Here is a texture of the current Falloff map. I didn't quite know how to visualize this, so I made a replica in good old Unity engine. Where in the texture is black, it means that the terrain can spawn. Where it is white, it means that the terrain will not spawn. Here you can see how influential the Falloff map currently is and why we're only getting a little piece of land. We can see that if we modify A, we control how smooth the transition is from black to white, thus controlling how sharp and accurate the Falloff map is. If we modify B, we can control how far away from the center the Falloff map begins to take precedence over the map. Now looking at the map, I can't help but notice that regions near the equator, namely North Africa, the Middle East, Central Asia, and the westerly regions of the US mainland, look a little deserty. As a challenge, I've decided to make an attempt at mimicking the deserty equator regions. This may be simple on paper, but the terrain is on a 45-degree angle. I will need to find the center of the terrain and then go left and right relative to the midpoint. The midpoint is simply calculated as so. Then we want to calculate the points on the prime meridian, points where the longitude is 0. I'll quickly skim over this in the interest of time. We want the points northwest of the midpoint for every equator influence this function has on the terrain. We'll use the index I as an offset to compute points northwest of the midpoint, check if the point is valid, and add it to the equatorial bounds. We'll also do the same for southeast. Then we want to compute every point northeast and southwest of the prime meridian until the edge of the map is reached. Keep in mind that despite the blocks having the cardinal and intercardinal directions in memory, this function is called before there are any blocks in the game, so all computations must be done numerically according to their index. Here we keep going northeast, and here we keep going southwest. By the end, we get the positions that make up the equator in compliance with equator influence. It doesn't look too great, but it provides some variation in the terrain. Polar noise is powerful, but I feel like it's being wasted on generating a static terrain. It'll be nice to see some sort of infinite generation of blocks. If we move the camera over the borders of the map, it will generate new blocks in the map and ensure that the terrain stays dynamic. To do this, we need to consistently update the position of the camera and check if we need to generate new blocks. And here is the code for that. And finally, the last thing that is procedurally generated on the map are warriors. More about their use later in artificial intelligence, but essentially these warriors will be attacking each other. As such, we can't randomly generate the spawn points of the warriors, as some may consider it as spawn camping. That is, what if a number of AI warriors surround a human warrior? The human warrior is at a major disadvantage as it can be immediately attacked in a single move. We need to spawn warriors a minimum space apart from another warrior. This can be done with a method called Poisson disk sampling, where the resulting points it returns is at least a minimum distance away from another point. Here is the code. We iterate for iterations before rejection to find a block that is traversable and does not lie in the T set of already occupied blocks. If it's not, add the surrounding blocks within a minimum distance radius to the T set and return the valid block. Obviously, this won't always work, given the iterations before rejection. Sometimes all the blocks will have been occupied and there is no other available block, in which case we will just select any at random and give a warning. The map may be too small, the minimum distance may be too large, or there are too many points that are being requested. For utility, the Falloff generator is done on a purely numerical basis, meaning that anyone can use the code, plug it into their polar noise calculation, and generate a terrain with a controllable falloff. Falloff isn't exclusively for generating islands though. Falloff, more generically, gets information about the edges of a grid. In our case, we can simply reverse this to generate an oasis of some sort. With my Falloff generator, it also comes with the transition equation that we've outlined before, which gives Falloff a high level of customizability. Poisson disk sampling is also provided in full. Poisson disk sampling is useful for when you want to spawn objects or players a minimum distance apart from one another, such as buildings or trees. In my case, I spawn warriors. Now, it definitely wasn't an easy implementation, this procedural content generation. I've simply left you with the final result, basically the answer to my past problems I've encountered, and I'm pretty sure that's for everyone doing any assignment. Producing continents, for example, made inaccurate results when coupled with computing a Falloff map. Some parts of the continents would seep past the restrictions imposed by Falloff, thus ruining the effect for both Falloff and continents. Generating the Falloff Map in the end was simply a mathematical formula, but was a headache to get around. In the end, I decided to come up with a weird function that allows the control of a Falloff Map. Computing the equator also caused a lot of trouble. It would be easier if there were information on the blocks about the equator, but the function needed to be constructed in a specific way, such that it would never acknowledge the existence of a block. It was full of really confusing numbers that looked simple in the end. There was also an issue with Poisson disk sampling and Unreal Engine's handling of static generic data types. From what I've observed, a static T-array, T-set, and T-map all preserve and maintain their memory throughout play. If I hit play, generate a 50 by 50 sized terrain into a static T-set, stop play, and then hit play again, the size of the T-set will be 5000 rather than the expected 2500. In essence, static fields have memory persistence throughout play until compilation. This was a huge hassle when finding occupied blocks in Poisson disk sampling, but to my knowledge, this issue was never mentioned in Unreal Engine forums. I think I'll leave the procedural content generation here. I'll leave you to the next part in artificial intelligence.